the stroke of 4, so good enough. So, I'm Richard Steenbergen. If you don't get enough of me in this presentation, I'm doing 3 this nanog, so you'll be seeing lots more of me soon. This is a repeat of a tutorial that I did in the Dominican Republic, and there was a lot of interest in it and a lot of belief that there wasn't enough exposure. So I'm redoing it, but with a little bit of tweaks, so hopefully it's going to get more exposure and be even more intelligible to people. So, we're talking about Traceroute, which is the #1 troubleshooting tool on the internet. Basically, every OS has a Traceroute tool of some kind. There's thousands of websites out there where you can run looking glass, where you can run traceroutes from different places. There's dozens of visual traceroute tools. There's people that don't know the first thing about routing, but somehow they manage to generate a traceroute, and somehow they also manage to find your phone number. So there's a lot of traceroute out there. And it seems like such a simple tool to use. I mean, you type in an IP address, you hit enter, you get a list of router hops, and the naive approach is wherever you see the latency go up, or you see a drop packet, or you see something like that, you go, oh, that's the problem, and then you call that provider and you say, fix your network. And the reality is it almost never happens that way. So, why doesn't it happen that way? Well, in reality, most modern networks are actually pretty well run. There's a lot less of the scenarios where traceroute used to be the final answer. There's a lot less routing loops. There's a lot less simple congestion. There's just a lot less of that. You don't see the simple problems anymore, or you see them a lot less. And there's very few people that are actually skilled at interpreting a traceroute. Most NOCs that I've dealt with, even their engineering staff to a degree, really don't understand Traceroute, and they think they do because, well, hey, look, I read, I know what routers are, and I read this list of routes, and I think that I know what the problem is. But there's a lot of subtle things that go on behind Traceroute that people don't understand. And what happens is, with this flood of people out there that are running this tool that don't really know how to interpret it, they end up flooding the NOCs with all these false reports. And if you've ever tried to submit a Traceroute-based ticket to a NOC, even if you're exactly right and you know that you're right, you can't convince anyone else that you're right, because they get flooded with just hundreds of thousands of these things every day. Why is my gaming so slow? Why is this not working? In reality, most people just don't know what they're talking about. So, the topics that we're going to talk about for Traceroute, we're going to talk about how Traceroute works in general. We're going to talk about how you can interpret DNS in Traceroute. We're going to talk about understanding the components of the network latency that you see in Traceroute, understanding when it's legitimate, when it's not, what the components are there. We're going to talk about what happens with ICMP prioritization and rate limiting on routers, why you'll sometimes see false badness in a traceroute that isn't really real. We'll talk about asymmetric forwarding paths, load balancing across multiple paths, and then finally what happens to Traceroute when it goes through MPLS. And there's a couple little gotchas in there that can look bad but really aren't. So, random Traceroute factoid. The starting port for a Unix traceroute is 33.434, which is 32.768, which is 2 to the 15th, plus 666, the mark of Satan. So I think there's some kind of coincidence there, but I'm not sure. So, how traceroute works. Here's the 10,000-foot overview. The source that's doing the traceroute launches a packet towards the destination, and they launch an initial packet with a TTL of 1. Every time a packet goes through a router, the TTL is decremented by 1. When the TTL hits 0, the router drops the packet, sends an ICMP TTL exceed message back to the original source with part of the original payload, part of the original probe that got dropped, the first 64 bytes, I think, as part of that ICMP. The source gets that ICMP back, says, okay, this must be a traceroute hop, and whatever the ICMP message source is, that's what it displays as the hop. So as soon as it's determined what hop 1 is, it'll do the same thing, but it'll start with a TTL of 2. It'll get a message back, it'll say that's hop 2, and so on and so forth, until it gets to the end. And when it gets to the end, when it actually reaches the end host, what it's supposed to do in classic UDP Unix traceroute is send an ICMP destination unreachable. So it hits a port that there's no one listening to, and then the end host says, there's no one listening here. It gets that ICMP message back, which is not the TTL exceed, and it says, okay, traceroute done. So there's actually a lot more detail behind that. There's many different protocols that you can use for Traceroute. I mean, actually, you can use anything that IP will route, essentially. But the classic Unix Traceroute uses UDP probes, like I said, starting at a destination port of 33.434. And every time it sends out a probe, it increments the port, and that's how it knows when it gets a message back which probe it's getting an answer to. It detects the end when it gets that ICMP destination unreachable. So if for any reason your end host is firewalled, if it's not responding to UDP, or even if there's a legitimate application listening on whichever port it happens to hit, it won't know that there's an end of a traceroute. And what will happen is I'm sure you've all seen this, it'll star out, it'll time out, and it'll get all the way down to the maximum possible hops that it'll try before it terminates the program. There's other implementations that do this with ICMP echo requests. The two biggest examples are Windows Traceroute, traceRT.exe, and MTR, which is a popular tool, which essentially just does traceroute in a never-ending cycle, like once per second. It just keeps sending them over and over. But it's ICMP echo request. It's similar to the UDP probes, except when it hits the final destination, it gets an echo reply back. So you might say that that's actually better than UDP because it doesn't, people are more apt to reply to an ICMP echo request than they are to a UDP probe to a random port that they're not listening on. Or they may not. They may actually filter that. So it depends on what the firewall is, what type of the end host is. And then there's other Traceroute implementations, like the stock FreeBSD Traceroute and a whole bunch of others, where you can specify which protocol you want to use. So you can use the TCP packets, for example. This is generally a poor choice for general use in a Traceroute because people are more apt to filter TCP packets destined to things that they're not interested to. But if for some reason someone is filtering ICMP and UDP, it might be a way to get around a firewall. So it's good to have options. Most implementations send multiple probes per hop. So classic Traceroute example, you see 3 results. It's sending 3 probes before it moves on to its next hop. And so you're going to get 3 latency results, or 3 stars if there's no response. Except for MTR, which is an example of one that just sends it in an endless loop. And when it gets to the bottom, it starts back at the top again, and it just keeps incrementing. So each probe has a unique code in it. When you're using UDP and TCP, you're using the layer 4 port. So the Traceroute program knows when it gets its response back which probe this was for. For ICMP, it's using a sequence number, but there's always some kind of code embedded in the packet. And layer 4 hashing can send each one of these paths down at different paths. So what happens here? Normally, flow hashing will try to keep a flow on a specific path. But when you're using an incrementing port, it thinks it's a different flow. So every time you send a probe, it can go down a completely different path than the previous one. So that's where you can start to see multiple results. If someone is doing ECMP, if they're doing load balancing at layer 3, you will see the multiple paths because you'll see different router hops. If they're using a lag, you won't see it in Traceroute, but it's still happening. The packets are still going down specific paths. And so consider the case where one member of a 4-member link aggregate group, a lag, is bad, and you start to see 1 out of every 4 packets drop. You have no visibility into that. To you, it looks like the same path, but it's not. It's actually going over different paths. And which path it goes over can depend on your IP address or your port. And so that's where you start to see people say, I'm having problems with this one application, but not this other application. Sometimes it's just random luck of the draw. Traceroute latency is calculated by the program that's launching the Traceroute timestamps when the packet went out. It timestamps when it gets the ICMP back, and the difference between the two is the round trip time. The routers along the path don't actually do any processing with the time. The routers along the path don't timestamp it, don't do anything. All they do is reflect some of the original packet back to you in its ICMP TTL. So you've got to understand that when you're looking at the round trip time, you're looking at both directions, even though Traceroute's only showing you the forward direction. And there's more on that later. So it helps to know what hops you're seeing in a traceroute. So here's a diagram of a simple traceroute starting from a single source going through 2 routers. And what you're seeing is the ingress router interface at every point. So, for example, in this case, the packet comes in, it's dropped by router 1. The address that it's going to send its ICMP back on, which is how Traceroute's going to detect the hop, is going to be the ingress interface, the 172.168.2.1 in this example. It's not going to show you the egress interface. It's not going to show you the return interface. It's going to show you the ingress interface. And then the second router does the same thing. So in this diagram, you can see the two hops that it's going to show you, and you can see the hops that it's not going to show you. You've got to realize that there's no visibility into the egress paths, the return paths. And another random factoid, this is actually a non-standard behavior. If you go look at RFC 1812, which as far as I can tell has never been updated, it actually says it should source from the egress interface of the ICMP, not the ingress interface of the original datagram. So it's kind of a weird de facto standard that we don't actually follow the standards, and that's what makes Traceroute work. So interpreting DNS and Traceroute is one of the most important things that you can learn to troubleshoot Traceroute correctly. Because from looking at DNS, you can figure out where these routers are located, be it city, state, country. You can figure out sometimes if it's in an Equinix facility or a PAX facility, or you can find out some details there. You can figure out what the interface type is, what the capacity is. You can figure out what the router type is. You can figure out if it's a peering router or a core router or a customer edge router. You can figure out if the network boundary and relationship, so you can see the demarc point between network A and network B, and then you can see, is this a transit relationship, is this a peer relationship, is this a customer relationship, and what you can deduce from DNS really is essential to figuring out what's going on in a traceroute. Why do you need to know geographical locations? Well, first off, you need it to identify incorrect or suboptimal routing. For example, if you're going from Atlanta to Miami and you see a hop in the middle in New York, there's probably a problem there, and that's probably some routing issue that you could get addressed. Sometimes high latency is justified. 100 milliseconds across an ocean may be the fastest path possible. Sometimes it's not. Sometimes it may be congestion. Sometimes it may be suboptimal routing. So you've got to understand what it should be, and what it should be is largely determined by geographical distance. So the most commonly used identifiers are the IATA airport codes, CLLI codes, silly codes, and then non-standard abbreviations that are kind of close to the English name, and then sometimes you just have to kind of guess. IATA airport codes are a good choice. They have a lot of international coverage. If there's a major city somewhere, odds are it has an airport. It has an airport code. It has a standard 3-letter code that's unique that you can use. It's not as effective as covering less well-developed areas, covering a large number of smaller cities. But if you're just talking about a handful of very large pops, it can be perfectly acceptable. So, for example, Dallas, Texas is DFW, which stands for Dallas-Fort Worth. You might not know that DFW is Dallas, but you can go look it up. You can go Google DFW, and you can see that it's Dallas. San Jose, SJC, etc. Sometimes these things are represented by pseudo-airport codes, where the airport code itself is not very intuitive, or where there's multiple airport codes. So, for example, New York is covered by JFK, LaGuardia, and Newark. But you might just see someone, rather than try to break it out into JFK and LGA, which might not be intuitive, you might see someone just call it NYC, which is actually a pseudo-airport code. It's representative of the entire region. Similarly, in DC, there's multiple. There's IED in Dulles. There's DCA in Washington, D.C. You might see that represented by WDC. The other option that networks use are silly codes. So the silly codes are the Common Language Location Identifier. It's a telco spec that's currently maintained and sold by Telcordia. It's intended for phone companies mapping all the way down to their CO and their switches and their panels and positions. But it has the very convenient attribute of the first 6 characters being a standardized, very, very well-maintained list of cities and states called geopolitical and geographical location identifiers, which make really good router naming conventions and things that you'll see in Traceroute. So for example, Houston, Texas, HSTNTX, and you can Google that and you can see that that's Houston, Texas. And it might also cover cities that are outside of Houston that don't have their own airports. So if you're talking about someone with a lot of smaller pops, you'll see silly codes used more often. Basically, they have very complete coverage of North America and very incomplete coverage everywhere else because it's a U.S. And Canada. It's a North American naming standard. So there's some providers that have actually made up, I'm not sure if there's any kind of standardization behind this at all, but I've seen some providers that have made up international codes that kind of fit the same thing. But it's primarily, if you're a North American-based network, that's where you're really going to see these. And then sometimes there's people that just make codes up. For example, sometimes the airport codes aren't very intuitive. So Chicago, for example, is served by two airports, O'Hare and Midway. And if you saw ORD and MDW, if you didn't travel a lot and you didn't know that these were airport codes, you might think, the hell is that, and what does that have to do with Chicago? So some people, for example, will just arbitrarily make up, we'll call it CHI. It's not an airport code. It's not any kind of standard. But they'll take the ones that are obscure and they'll turn it into something that's a little more English friendly. Another example is Toronto, where YYZ or YTZ, these things might not mean anything to anyone that didn't know airport codes, and so they might turn it into TOR. And it's generally based in good intentions. It's based in people that are trying to make things readable and understandable. But the downside is it doesn't actually follow a standard, so you can't necessarily Google it, but maybe you can just kind of figure it out on your own. So I have a list of the major U.S. cities that are important for IP, and the airport codes that you might see, the silly codes that you might see, and a lot of the common names. So for example, Dallas is another one where DFW might not make sense, but some people will call it DAL. And you can kind of try to reverse engineer that. But I put this in there as kind of a reference guide for people who are looking at Traceroute, trying to figure out what's going on. They can look at this and see where the packets are. And then here's the non-US cities. And the silly codes here I took from NTT because they have a fairly comprehensive list of them. And like I said, I have no idea if there's any kind of standard behind those or not. I don't think there is. But there's an example of someone who's using them. And generally speaking, you can kind of read those and insert some vowels and figure out what the city name is. The next thing you can interpret in DNS is the interface type. Most networks will try to put interface info in DNS unless they're Google, and they won't for some inexplicable reason. For the most part, it's to help people troubleshoot their own network, honestly. No one has a handy directory of what this IP is to what this router is, and so someone internally will run a traceroute and then they'll figure out where their own router is and they'll go look there. But it's also helpful for people on the internet in general. It may not always be up to date. There's some surprisingly large networks who don't keep their pointers up to date at all. An example is AT&T is very bad about this. There's others that are completely script generated where there'll be a program that nightly runs through the router in ICMP and sets all the DNS pointers based on what the routers actually are. I think that's a much better way to do that, and it's surprisingly simple to do that. So I mean, I really encourage anyone that's running a big network to take the time to set their DNS correctly because it's helpful. You can help figure out the type of interface, and sometimes you can even figure out what the make and the model of the router is. So for example, this is a real example from level 3. XE-11-1-0 is the XE- is a naming scheme from a Juniper router, and because it has the second number is not a 0, that means that it can't be a single port, a single slot card. It has to have at least 2 10 gig ports in there, and because it has at least 12 slots, you pretty much know that it's a Juniper MX960. No other router happens to fit that naming scheme. So I have a list of naming conventions here that you're most likely to see. There's the standard naming convention that Cisco uses, which is basically the first 2 letters of the interface name. So like FastE, some people would expect that to be FE. Cisco uses FA because it's the first 2 letters of fast. GI for gigabit, same thing. But you'll see these codes used in DNS because that just happens to be the standard. And it helps you figure out, what link speed this is, what type of interface this is. It can really help you figure out if this is just an oversubscribed link, or if this should be going here, or this shouldn't be going here. So it's good to know. And the only real disclaimer on here is some of the early Juniper 10 gig interfaces, for some unknown reason, were actually named GE instead of XE. But they fixed that in later revisions. So if you see that, if you see a GE, don't necessarily think, oh no, it's a giggy. It might actually be a 10 gig. The other thing you can determine, obviously, is the router type and roles, which can be pretty helpful. Problem being, every network has its own naming convention. A lot of the times you just have to either have some idea about the network or kind of guess. If you start to see things that are core router, core, gigabit backbone router, backbone, core, Ethernet backbone router are some examples. Some of these might not, you might look at EBR and think border router, unless you happen to know that it's an Ethernet backbone router. So some of these things are very confusing, and really it's the kind of thing you build with experience and knowing these networks, is knowing what type of router you're going through on their side. A lot of peering routers are called border routers, borders, edge, internet routers, interconnection routers, internet gateway routers, peers. A lot of customer routers are called aggregation routers, aggers, customer routers, customer access routers, high-speed access, gateways, things like that. These are very common naming conventions. The next thing that you really need to identify, and this is probably the most important aspect of Traceroute, is figuring out network boundaries. The reason being, network boundaries are where the policies tend to change. So, for example, when you cross between level 3 and AT&T, they're going to have completely different routing policies. And the instant that packet gets off level 3's network and goes to AT&T's network, guess what? You're going to expect a different return path because they have different routing policies. So identifying these things is really helpful to figuring out what the problem is. It's also an area where interconnection capacity planning is hard, because it's two companies who are working together. So it's not just some internal process. There's more work involved. So there's more likely to be issues there. And it also, you need to know who to blame if you're going to open a ticket. So identifying the border boundary and identifying who is at fault is important and very often overlooked. And then you need to identify the type of relationship, or you can, be it a transit provider, a peer, or a customer. The best networks that make this very explicit in their DNS, they'll say something like customer name.customer. It really helps to know this is a DMARC. This is not my router. This is the customer's router. So here's some examples. Sometimes it's really easy to spot where the DNS changes. Hey, look, this was formerly GBLX, and now it's Brent, and there's the border. Other times, it's not so easy, but you can look for the other party name. So, for example, hop4 is GBLX. hop5 says Cogent in it. Even though the name says gblx.net, this is actually Cogent's router. This is the IP that's responding is Cogent's router, not GBLX's. It just happens to be the border. Sometimes there'll be no DNS at all, and you have to figure out, for example, in this traceroute, is hop3 the border, or is hop4 the border? You might not know. And in this way, in this example, what you can do is you can look up the IP and who is, even though it has no DNS, and you can see, well, that's owned by AT&T, so that's probably their border. The next thing that you can really do to help figure this out, and this is kind of dependent on people using /30, so I'll throw out the disclaimer that more and more people are using /31s, so you should watch out for that. But if they are using /30s, you can very easily figure out what the other side is and go look up the DNS on that, and that will give you a lot more details. So in the previous example where we were talking about a traceroute here where hop5 says cogent.whatever, you can go look up the other side. If you I can just do this in my head, but if you can't, there's a program called IPCalc, or there's various web pages where you can go type in an IP and it'll tell you what the base interface. So in this case, it's 64.212.107.88/30, and so 89 is one side and 90 is the other side. So you go look up 89, and you see the egress interface on Global Crossing. So you have a really good understanding here from looking at this. You can see that the packet came into their AR5.DCA3 router over port channel 2, and it went out over 10 gig 2/3, and then the other side of 10 gig 2/3 is cogent. So even though it says cogent in that DNS, even if it didn't say that, you should be able to look at this and determine this is a demarc, and if there's a problem, if there's, for example, high latency starting at hop 5, it's probably not Global Crossing's fault, or it very well may be, but it very well may be an asymmetric path. So this kind of thing is common with private peering. What happens is when you turn up a peer, it'll pretty much be a flip of the coin. Who gets the /30, me or them? And one side will give up the /30, and they'll be one IP, and the other network will be the other IP. But what they won't do a lot of the times is get DNS information or maintain DNS information. So what will happen is, rather than put the other side's information in DNS, they'll put their side twice. And sometimes put a little identifier that says cogent, but sometimes they won't. So you got to look for that kind of thing to figure out where the demarc is. Next most important thing, understanding network latency. So this is a big source of the traceroute submissions that we get. Basically, there's three main sources of network latency that you should care about. The first is serialization delay. Basically, that has to do with the delay of moving the packets through the internet in packet-sized chunks, because you can't start transmitting the next packet until you've finished with your first packet. So there's going to be movement in discrete networks through the network, and there's going to be some delay associated with that. There's queuing delay, which is the time spent in the router's queues waiting for transmission, and this is mostly related to full interfaces. There is a need for queuing that has nothing to do with full interfaces. Queuing does serve a useful function, but when it happens without the interfaces being full, you won't notice it. If you notice queuing delay, it's because the interfaces are full, realistically. And then the third one is propagation delay, which is the time that the packet spends in flight on the wire, and that's basically a limit of the speed of light and electromagnetic propagation. So I have some details on serialization delay. It's not much of an issue in modern networks. I mean, basically what's happened is link speeds are now many orders of magnitudes faster, and packet sizes have stayed the same, and so it doesn't matter anymore. You run a 1500 byte packet over a gigi network, and it's 0.012 milliseconds, which isn't an issue. Whereas if you ran that over a 56K link, that would be responsible for 214 milliseconds of your delay, purely encoding the packet as a packet-sized unit. Queuing delay, so I have some details about that. Basically, when most people talk about utilization, they're not actually talking about utilization the right way. When you say, I'm doing 500 megs on a 1 gig port, you say it's 50% utilized. But what you actually mean is it's 50% utilized over 1 second. Because at any given instant, an interface is either utilized, it's transmitting, it's 100% full, or it's not utilized, it's not transmitting, it's 0. And so you're looking at utilization over some period of time, which we talk about 1 second, but in reality, in these fractions of a second, if the interface is in use, you have to queue the packet for however many fractions of a second until the interface comes up. So the odds of the interface having to queue go up exponentially as the link gets fuller over time. So if you're using 90% of the interface on a per second measurement, there's a very good chance that at some point an interface is going to get, a packet's going to get queued. And as it approaches saturation, as you get in 98, 99, 100% saturated, what happens is the length of time that the packet has to spend in the queue to look for an open slot in the transmitter rises exponentially, and that's where you start seeing many hundreds of milliseconds or thousands. The packet still gets through, it just has to wait a really long time to find an open slot, and effectively that's a full interface. And then propagation delay, which is the biggest source of most of the complaints, and the best thing that you can answer is say, take it up with God, because I didn't set the speed limit. Or the answer that I give is, you can tell God wasn't a gamer. Basically, light will only travel so fast. Light in a vacuum goes 300,000 kilometers per second, which is pretty fast, but not fast enough. When your fiber goes through glass, which is not a vacuum, it's going through, I left out the details of how fiber works, but basically what's happening is it's refracting inside this fiber continuously. And so it's going through the core of the fiber, which has a refractive index of 1.48, which means that it travels at about 2/3 the speed of light, which means that it's about 200,000 kilometers per second. And if you divide that out or multiply that out, it's 200 kilometers per millisecond per direction. And if you take into account round trip time, because that's what Traceroute measures, for every 100 kilometers, or 62.5 miles, that a packet goes out and comes back, is going to be 1 millisecond of propagation delay due to speed of light. So, for example, if you were to go around the world at the equator via a perfectly straight fiber route, it'd take 400 milliseconds. And what are you going to do? So, how do you determine if the latency is normal? You've really got to look at the geographical data and figure out if the latency fits with propagation or if it fits into queuing delays. So, for example, in this trace route, 67 milliseconds, but you're going between New York and London. That's 4,200 miles, and so this is actually the fastest commercial route that you can buy. You can't get any better at the speed of light. There it is. And the only way to reduce that latency is to either move one of the two parties closer. Another example here, for example, is AT&T in Washington, D.C. going to Cogent in Washington, D.C. 228 milliseconds. That's not normal for Washington, D.C. to Washington, D.C. That's probably the result of either congestion or an asymmetric path. So you can immediately rule out propagation delay there. So the next big issue when it comes to analyzing traceroute is cosmetic delays, because the time taken, the latency value of traceroute is determined by the time taken for the packet to get to the router that drops the packet, the time taken for the router to generate the ICMP, and the time taken for the ICMP to get back to you. So items 1 and 3 are actual network conditions that you're trying to measure. Item number 2 is, by definition, not. It's an artifact of traceroute. And so if there's an issue where the router is slow in generating the ICMP message, it will look bad in traceroute even though it's not actually bad to the packet. And so you've got to kind of figure out when that's happening and when that's not. So basically the big issue here is to it versus through it. Modern routers have what's called a data plane, which is how packets forward through the router, and a control plane, which is where your routing protocols run, where your CLI runs. But even within that data plane, there's a fast path and a slow path. The fast path in a modern router is implemented in hardware. There's an ASIC that forwards, millions, hundreds of millions of packets per second, and that's almost every packet that goes through. Then there's a slow path, which is handled by a CPU, and it handles things that are weird, random exception packets that can't be processed in ASIC. So examples of that are IP options and ICMP generation. And traceroute happens at ICMP generation. So by definition, your traceroute is going through a path that is not the same as a normal network forwarding. And basically what happens is the router CPUs tend to be pretty underpowered. You may have a router that does 640 gigs of traffic that might be processing traceroute with a single 600 megahertz MIPS CPU that's doing other things besides processing traceroute. And what happens is, in order to keep the router functioning, the software will intentionally depreference the ICMP generation. It won't do it unless there's available CPU. So what happens is the most common example is what's called BGP Scanner. So BGP Scanner is a process that runs on Cisco iOS every 60 seconds. It does some periodic cleanups of BGP routes and next hops. But what happens is every 60 seconds when that runs, that consumes CPU that's no longer available to generate ICMP. So these routers, a lot of the times, they're sharing the control plane and the software plane. For example, one of the most popular platforms, the Cisco Catalyst 6500 and 7600, it's sharing your CLI, your BGP, all your routing protocols, and ICMP generation on the same processor. And that one processor is for the entire box. So someone types a big show IP BGP complicated regex command, and all of a sudden your traceroutes get slow. Or this periodic process runs, and all of a sudden your traceroutes get slow. The BGP scanner, there's actually some optimizations in new code called next hop tracking that kind of reduces some of the impact of that. So if you get a chance to upgrade your routers to modern code, you can take advantage of that, and it'll help at least reduce the impact for that one particular process. The other issue is that most routers actually rate limit the ICMP generation, and a lot of the times they do it with hard-coded arbitrary values that you can, as a user, can't change. And these values may not be sufficient under heavy traceroute load, especially with more and more people running MTR, which, like I said, just runs the traceroute over and over and over and exhausts the router resources. So I broke it down by some of the most common platform types. So the Juniper MT-MX series is distributed ICMP generation. It happens on the FPC CPU, so it doesn't touch the routing engine, but there's a hard-coded limit. There's a hard-coded limit of it depends on the type of FPC, and they've changed it in recent versions, but they haven't bumped it. It's not configurable. It's not explicitly clear what some of these values are, and for certain old routers, it's still a very low limit. So 50 packets per second, not much at all. If someone has an actual forwarding loop somewhere, like just some random user configures a static route that creates an actual forwarding loop, your box may suddenly stop doing traceroute because it's overloaded. Foundry. The MLX and XMR platforms have a hard-coded limit of 400 packets per second per interface. Force 10 has a hard-coded limit of either 200 or 600, depending on the type of interface. Cisco is actually one of the only platforms where it's not hard-coded, but the downside there is that it's centralized. So it's not distributed per line card. It goes to the central, on the 6500, 7600, it goes to the central control processor. So you can configure the rate limit wherever you want, but it's probably not going to do as many packets per second as a distributed platform where you can't configure it. The GSR is hard-coded as far as I can tell, even though the ICMP generation is done on the line card, so it's the same as Juniper. And apparently on new software on CRS1, you're able to do some type of configuration. And the only example that I could get from anyone was for MPLS. TTL expirations, and I'm not sure if that applies to other packets or if there's another option outside of MPLS, but there's at least some configuration option. The point being, these aren't very clear, explicit, and if you have a big network, you're very likely to bump these limits where all of a sudden, even though your router has available processing resources, it's not generating trace routes, and people start opening tickets. So, the number one rule for spotting fake latency is if there's an actual issue, the latency has to continue for all hops forward. So in this example, there's a latency spike in the middle of hop 2, and it didn't take me very long of running trace routes to hit this because it basically happens all the time. But you look at this and you say, okay, well, there was a latency spike there, but it didn't continue through the next hop. So you can look at this and say this is cosmetic, because if there was an actual issue that was causing 68 milliseconds, you would see that increased latency in hop 3 and hop 4 and hop 5, and if you don't, it's fake. And that eliminates about 80% of the traceroute tickets that people will submit if they just understood that one rule for telling what's an actual issue and what's not. But it could also mean there's an asymmetric path. It could mean there's an artificial rate limit. It could mean anything. It could actually be an issue, but it's an issue that only affects traceroute. It's not an issue that affects real packets. So the next big issue with traceroute is asymmetric paths. Basically, the internet has absolutely no guarantee of symmetry. And in fact, if there's a guarantee of anything, it's that your paths are not going to be asymmetric. Traceroute is only showing you the forward path, but your latency calculation is based on the return trip time. So there's this invisible component to traceroute that you can't see that's affecting your results. The only way to figure this out is to get a traceroute in the reverse path. The problem is, it's actually possible for the paths to be asymmetric at every hop along the path. So even though you may get a traceroute from side A and you may get a traceroute from side Z, there can be hops in the middle where the paths don't take any of the paths that you've seen. And this doesn't affect your actual forwarded traffic, but it affects your traceroute. So you need to understand when you'll see cosmetic problems and when you won't. So here's some examples of cosmetic problems, or asymmetric routing problems, I should say, where you see between DCA3, which is Ashburn, Virginia, on Global Crossing, and Ashburn and Sprint, so within probably the same data center, you see a 100 millisecond spike. So you look at this and you say, well, what's the problem? What could be going on here? It could be congestion between Global Crossing and Sprint, where Global Crossing's interface is full, it's queuing packets. If you happen to know anything about Global Crossing's infrastructure here, you know that AR3 is a Cisco 7600 that doesn't have a buffer that could hold anything close to 100 milliseconds. So right off the bat, you know that that can't be the case. So it pretty much has to be an asymmetric routing path. You see that this is a border. This is where the packet goes from Global Crossing to Sprint. So now Sprint's routing policy takes effect for that return path, and so you need to figure out what's going on. I have these kind of out of order, but so here's an example of how you can. Well, actually, let me explain this more. So basically, asymmetric paths can happen at every hop. So here I've illustrated packets going through a network that interconnects two networks that interconnect in 3 locations, interconnect in DC, Chicago, and San Jose, which is vastly simplified. And there's 3 traceroute hops. So hop 1 is purple, hop 2 is red, hop 3 is green. Hop 1, the packet goes out in Washington, D.C., comes back in Washington, D.C., goes out the same interface, comes back the same path. Hop 2, hot potatoes out the network, it goes to the other router in Washington, D.C. They haul it to Chicago. The traceroute drops the router drops the packet, generates an ICMP TTL. That TTL goes back via the Chicago interconnection. Hop 3, it goes all the way out to San Jose. It drops the packet. It generates the TTL. It comes back via the San Jose interconnection. So you've now seen 3 different reverse paths that if the final destination was LA, for example, and the packet went out the LA destination, none of your traceroute, either direction, would show the path going through either one of these 3 interconnections, even though those might be where the problems are. So if, for example, there was congestion or there was packet loss or whatever on the Chicago interconnection here, or the Chicago return path, you wouldn't see it in traceroute, and it might only affect the middle hop, and then it might go away for the hop after that. And you have to be able to tell what's going on there, whether that's cosmetic or whether, in this case, it's an actual problem, but it doesn't affect your real traffic because only your traceroute traffic goes over this bad path. So there's some ways that you can kind of test around asymmetric paths. So consider the previous example that I had where I said that in this scenario your network is connected to Global Crossing and Level 3. When you send a packet to Global Crossing, it comes back via Global Crossing. When you send a packet to Level 3, it comes back via Level 3. But how do you reach Sprint? In this scenario, you send the packet to Global Crossing sends the packet to Sprint. Now the packet is on Sprint's network. How does it get back to you? Well, Sprint's policy is completely different than either one of these 2 networks. And so Sprint's policy, for whatever reason, says we'll send it back via Level 3, which is perfectly legitimate. But say there's a problem on that reverse path. The question is, how do you prove whether the issue is between Global Crossing and Sprint, or between Sprint and Level 3, or between Level 3 and you? There's a wide variety of places where the problem could be. So one of the quick and dirty ways to test around this when you have transit providers is to use the /30 that they've provided you as a source address. Because what happens is, say when you turn up a transit port with Global Crossing or Level 3 or whoever, they're going to give you a /30 out of their IP space. So if you go to your router and you set your traceroute source to be that IP, you will guarantee that this traffic is going to come back via that provider and via that return interface. It's not going to come back via some other interface in your network. It's not going to come back via some other provider. And so you try different source addresses based, from different networks, from different places in your network to kind of figure out what the return path is, even if you don't have a host in Sprint's network somewhere that you can run the traceroute. But what happens when the /30 is numbered out of my space, as in the case of a peer or a customer or potentially a peer, where your peers probably have a 50-50 chance of it being your space or their space? you can still see some benefits here just by trying different /30s. So for example, if you set it to your /30 instead of your loopback address, what you might be forcing the peer to do is to come back via that one interface. So in this example here, if I were to set my traceroute source to the interface in Washington, D.C., where I'm sending the packet, I might force the peer, rather than return the packet via Chicago or via San Jose, I might force them to return the packet via Washington, D.C. So you can go through each one of these interconnection points and test this out and see what the problem is. And things you have to know about trace routing from the router. The default source address on most routers is going to be the source address of the egress interface that the probe leaves from. In Cisco, there's no way to change this. I don't think there's a way to change this in Foundry or any of the other Cisco-like platforms. In Juniper, there's a way to change it by setting system default address selection. But by default, when you get the box out of the crate, it's not going to do this. So you need to know what your source address is to figure out what the return path is going to be. And there's also some issues with clock granularity. There's some platforms, for example, Cisco iOS, that can only look at packets within a 4 millisecond granularity. So you see the packet go 04, 04, 04. In reality, it might be 12, 12. It's just the clock is not accurate enough to make that determination. So you've got to understand when you run that trace route from that platform, you're not going to get accurate results. The other big issues that come up with traceroute are what happens when you load balance across multiple paths. So here's an example of equal cost multipath routing where router A can load balance between two different paths. It can go to B1 or B2. And what happens is TCP, UDP flow mapping will try to keep an individual flow between any two pairs that are transmitting data on a single link. The reason you want that to happen is if it were to send, say you're starting up your web page loading and it were to send one packet over link A and one packet over link B, what might happen is the packets might get switched along the way. And when TCP receives the packets, if it receives 1, 3, 2, at the moment when it receives 1 and then receives 3, it goes, oh, 2 got dropped. And it thinks that there's packet loss in the network and it throttles back. So you'll get very slow. The packets will still get through, but you'll get very slow performance. And a lot of the cause of slow performance on the internet, sadly, there's a dozen different bugs that can cause packet reordering. And this is actually a pretty common scenario. So people try to design their routers for this not to happen, where it's always going to send a particular flow down a particular path. Like I said earlier, when you're running traceroute and you're using the standard UDP or TCP probes, it's going to look like different layer 4 flows for every probe. And so you're going to see both paths. In this example, here's an example of Telia load balancing between two different pairs of routers along the way, and you'll see the packet for one path, and then you'll see the packet for the other path, and it's the same hop. It's the same 6 hops in, but it's parallel. So you look at this and you understand that there's ICMP load balancing going on. So here's a slightly more complex example where it can kind of get weird, but you just have to look at this and understand that this is ICMP between somewhat parallel paths. In this case, there's a path that goes Ashburn, New York, Seattle, and there's a path that goes Ashburn, Chicago, Seattle. There's nothing inherently wrong with this. Everything works. One path may be higher latency than the other. In this case, it's about 5 milliseconds higher to go via one path than the other. But it's the only thing that's happening here is the traceroute might get confusing. You might look at this and say, Ashburn, New York, Chicago, what? That's not actually the case. It's parallel paths. The place where it really gets screwy is when you have multiple unequal length paths, and this should really be avoided. There's potentially scenarios where you might configure your network to do this, but you should really try to avoid it because it makes traceroutes a complete disaster. So what happens in this case, basically when you have unequal length multipath, it makes the packets look like they're hopping back and forth. So in this scenario, we have router X inserted in the middle here. And so it's gonna cause future trace routes to go DCD, EDE. It's going to look like it's going back and forth, back and forth, back and forth. And if you actually look at one of the trace routes, I didn't even paste it in here because it's so nasty, it's not even funny. You really want to try to avoid setting up this scenario in your network. But if you ever see something like that, the best thing that you can do is to configure your trace route to only look at a single path. Every trace route implementation has some way to change the configuration to where it only sends one probe. And if you only send one probe, you only get one path. So you might look at it one path at a time. And then if you need to try out the other paths, a good way to do that is to increment your destination, your source or your destination IP by 1. So if I run a trace route over a single path to x.x.x.1, then I might run the same thing to .2, .3, .4. And every time I do that, it changes the hash computation, and so I might end up on a different path. And you do this until you find the path that you're looking for or to explore all the different paths. But this is how you do these probes one at a time instead of intermingling them, and then you understand what the paths are. And then the other screwy thing that happens with Traceroute is when you start getting MPLS in the mix here. The biggest problem is MPLS ICMP tunneling. So what happens is you have large networks who are running an MPLS core, and they run an MPLS only core. They don't even carry an IP network in their routing tables. There's not really any benefit to doing this. They happen to do it for whatever reason. And it's fine for switching MPLS packets, but the problem is what happens when you don't hide the traceroute hops in MPLS, but you don't carry an IP table in your router. So when you drop the packet and you generate the ICMP, where do you send it? You don't know. You don't have a routing table. So the workaround to actually make the packet get delivered is called ICMP tunneling. Well, what happens if you drop a packet due to TTL exceed inside the LSP and you generate an ICMP for it, you stick the ICMP back inside the LSP that you got the original packet from. And so that packet's going to go all the way to the end before it comes back to you. And it makes your trace routes look really weird. So, you can kind of discount the previous scenario where each hop had an independent return path, and now each hop goes all the way to the end of the LSP before coming back to you. It makes your trace routes look like this. So in this example, you might look at this and go, Palo Alto, Global Crossing, some hop that's not in DNS and AT&T, and then AT&T in San Francisco, and I'm going to 74 milliseconds. So you might go, AT&T's congested, there's some horrible problem, what's going on, Palo Alto to San Francisco shouldn't be 70 milliseconds. What's happening is ICMP tunneling, because you see it's 74 milliseconds every hop all the way through to the end in New York, which happens to be 74 milliseconds away. So when you see something like this where the latency, even though the distance gets further and further away but the latency stays the same, it's a dead giveaway that it's ICMP tunneling. And that is pretty much all I have, and I will take questions. Might want to go to Mike.
So for the load balancing, even if you send a single probe, if you have several paths, so to say the first hop, say you have two paths A and B.
Mm-hmm.
The first hop will go to path A. The second probe out of that probing session will go to the path B, and then they could go back and forth, and you could get this topology that looks like that it's going from path A to path B back and forth.
Well, you can. Basically, the point being there is no path A and there is no path B. There's paths however many there are. Yeah. And so when you set it to a single probe, you're looking at a single path that you're taking. So it might, in this scenario, it might go router A, router B2, router C1. It could happen because at router A, it could make that determination that it hashes onto a different flow. And so you're not looking at this and saying this is the trail of directly connected routers, but you're reducing confusion because you're not going B1, C3, bingo, what's going on here? Yeah. You're at least seeing a single consistent path through the network that your particular flow happens to be taking. But yeah, you're not guaranteed. If you go to B2, you're not guaranteed to go to C2. Your next hop could be C1.
Topology. You're not guaranteed to get the
right.
accurate topology.
Exactly. Yep. Anybody else? Okay then. So the ways that you can see the reverse paths, you can do it with IP options, and the problem is it's really not a reliable way to do it. You can do you can actually have the packet record inside the packet record the hops that it goes through. The problem is that almost every network turns that off because it's CPU intensive on their routers. And it's weird non-standard thing that no one uses. So people turn off the IP option processing. It really doesn't work in any kind of reliable way on the internet to figure out the reverse paths. One of the things that I've been pitching, which I think I saw someone propose to the IETF, but I'm not sure, I don't have any details on it, is some kind of protocol where you can request the reverse path. So I might send a request to your router along the way that says, hey, you, generate me a traceroute packet and send it back to me. And so you could use something like that to figure out the reverse path along the way. And that's just a question of, can it be designed securely, and will people implement this? There's nothing that's out there today that works, but it's a good theory for a way to fix this problem in the future. That's all that I've seen. Anybody else? Going once, going twice, sold. Yeah, definitely.